Hello, my name is Kevin Winters, and I am a graduate student here at the University of Rhode Island in the College of Engineering. And this is my MCE 551 Fluid Mechanics final project. Now, my project was a computational fluid dynamics analysis of flow around a submarine. Now, computational fluid dynamics, otherwise known as CFD, is an extremely useful tool used worldwide by engineers, which allows them to simulate and analyze fluid flow around or through an object or structure. It's due to these nature of these simulations, it's very interesting to the Navy and specifically to naval engineering, where CFD is the driving factor of many advancements in naval technologies and structures. The analysis of fluid flow around complex structures such as submarines is a challenge that is actively being explored by these naval engineering institutes. Submarines represent a unique challenge due to their intricate hydrodynamic interactions with the surrounding water. So the goal of the CFD is to look into the fluid dynamics governing a submarine's behavior in fluid flow by analyzing the results regarding velocity, vorticity generation, boundary separations, as well as pressure. CFD is very important in industry as well as education. It enables the optimization of many designs, and it's very cost effective in prototyping since a physical prototype does not need to be created. Simply an idea can be modeled and analyzed and compared to other models. So in order to perform this computational fluid dynamics analysis, a model first needed to be constructed. So here is the model that I created. It is a submarine, and it was simply made with curved lines and extrusions revolving and basic extrusion. And this model is made in such a way that the edges all met up and formed one solid part in order for the simulation to be functional. This design here is based on a Type 212A class submarine, and that is a German-made submarine. In order for the SolidWorks flow simulation to work, I needed to create this rectangular cylinder that encapsulated the entire submarine. And within the flow simulation add-in, there is an option to create lids. So adding lids to the front and back end of this rectangular cylinder, you can add boundary conditions to these lids. And for the frontmost lid towards the nose of the submarine, a boundary condition of inlet velocity was added. And then the back lid towards the rudders, a boundary condition of environmental pressure was created, or defined, you could say. And what this does is it simulates flow going from the front of the ship towards the back. So this simulates a submarine flowing through open water. Now, once the simulation has been run and you've set your global mesh and your mesh as well as the boundary conditions, once the button is pressed to hit run, many calculations happen within the program. So I did a little bit of a dive into the numerical method that happens within SolidWorks, and I have discovered that the numerical method that is performed by SolidWorks Flow Simulation employs the finite volume method in order to solve the FOB-averaged Navier-Stokes equations. Now, the FOB-averaged Navier-Stokes equations are derived from the Navier-Stokes equations, which involve the FOB-averaging process. Now, what is the FOB-averaging process? What it does is it takes into account the variations in the values such as velocity or density and temperature, and it separates these values into average and fluctuating components, and it adds them together, and you can compare them and have them separate values. And what this is happening here, what this slide shows, is you take the original governing equations and you use the FOB averaging, and this is the output here. After completion of the simulation, once it is finished running and the pop-up window has been completed, the next step is to look into the results. Now, 2D and 3D results were looked at in this project, and in order to get 2D results from a 3D model, which was created. I used something called cut plots. Now, cut plots, you can take a cross-sectional area and look at the behavior of the fluid that surrounds the submarine. So here in these two images, we can see the velocity and vorticity plots. These are the two cut plots that I did, which are 2D plots, as you can see. Now we can kind of go into this here and take a look at the first plot on the top, the velocity plot, which is inches per second. So going from left to right here, we can see on the green in front of the nose, this is our inlet velocity. So this is before it has interacted with our structure whatsoever. As the fluid begins to pass by the nose of the submarine, we can see some acceleration, some increase in velocity as the flow or the fluid is being pushed around the submarine. And on the bulk of the underneath of the submarine, we can see this higher velocity, as well as above the sail, which is the top part of the submarine, we can see an increased velocity. Now behind the sail, as well as past the rudders around the back end of the submarine, we can see lower velocity zones, even going to what seems to be zero. And this is due to a couple of reasons. Flow direction, as well as the geometry and shape of the structure. So the flow is going at a certain velocity in a certain direction, shape goes in, and the flow needs to be able to compensate for that, as well as the effect of flow separation and reconvergence. Once these flows separate around the sail and meet back, that creates some complex flows, which can result in slower velocities. Now, this is something that also goes into the second plot here, which is vorticity. Now, there's two major points here that I want to bring up, and the first one being at the very bottom of the submarine here. We can see that there is a considerable amount of vorticity generation that happens after the curve becomes flat, shortly after the flat part starts there. This geometry, or this change in geometry or shape, it can induce complex flow patterns, which result in this vorticity generation. As well as behind the sails and behind the rudders, yet again, we see a considerable amount of vorticity generated. This can be due to the flow separation, which we talked about earlier, and the reattachment of this flow, as it can often result in many complex flows. It's also important to note that the turbulence in the flow and the shear that's near the surface of the submarine can also contribute to the vorticity. Now, that becomes interrelation here on our first 3D plot, which is a surface contour plot. In this case, this one being velocity. Now, upon inspection, you'll be able to see that the entire surface of the submarine has a velocity of 0. Now, this is due to the fact of the non-slip condition, which happens to be true in the simulation, and it's an idea that we use in fluid mechanics in order to run calculations and to say that fluid is not simply just slipping across an object, and that there's some friction there, and that there's no slipping. And next, in these last two plots here, we can see vorticity and pressure plots. So for the vorticity surface plot, it shows similar results that we found in the cut plot. However, the surface plot shows us more than we could have seen in the 2D plot. In this case, the sail planes being those two small planes on the very top part of the ship, and that controls its depth and heading. Here on these sail planes, we see higher pressure zones or lower pressure zones, sorry, due to the flow separation and increase in velocity. In regards to the pressure plot, which shows the pressure across the surface of the submarine, on the left there are 3 points of interest to me. There's the first being the nose of the ship, where there's a high pressure zone. This is due to the submarine accelerating into the oncoming water out of the way, and the submarine's hull results in this higher pressure. And we also see a similar phenomena there at the front edge of the sail. It's rather small here, but there's red there. For the sail planes, we see low pressure above and below to the same principles of aerodynamic lift experienced by an airfoil. So as the flow passes over and under the sailplanes, the flow accelerates, leading to a decrease in pressure. This CFD analysis of the model's submarine's fluid mechanics provides a lot of insight into the performance of this vessel through methods of finite volume method and flow simulation. These aspects of the fluid behavior, such as the velocity and vorticity patterns, as well as pressure distributions that we explored earlier, all of this information is uncovered through this project, and the information found here has a lot of practical implications for naval engineers involved in submarine design and optimization. Through use of these simulations, designs can be analyzed, compared, and improved to create optimal designs, which could potentially enhance real-world situations. And not only does this analysis and this process deepen the understanding of fluid mechanics associated with submarines or whatever is being studied, but also the importance of these simulation tools to the industry. Thank you.